All right, good morning, everybody. So in this video, we are going to start looking at how double angles can come up in the solving process. So first on example 6, we are looking for all exact solutions. So exact meaning we're going to be using the unit circle on the interval 0 to 2 pi. So that tells us that we are looking for exact solutions in the units of radians. Now, if I look at this expression, the first thing that should jump out to me is that this is a quadratic trig expression. Now, the problem with this one is I have two different trig variables. So two different trig, you can call them variables or functions. But this goes back to that issue we had on the previous page where anytime I have two different trig functions in the same problem, I'm usually going to have to try to factor, usually by taking out a GCF in order to solve. So that's one of our first issues in this problem, and it's going to help us once we start looking at that double angle stuff. The second issue in this problem is the expression for the double angle, cosine of 2x. Now, the most important thing about those double angles is anytime you see a double angle, you replace it. So you can never just work with this expression cosine of 2x as is. You have to replace it with something from your formula sheet. So unfortunately, it's not as easy as this. Cosine of 2x is not the same as 2 cosine x. It's also not the same as cosine squared of x. So sometimes students will try to divide out a cosine from both of these. I cannot take a cosine out of 2x because this is as different of a variable as this one. So this would be like having x squared, then y, then z. So entirely different trig function units here. So I can't combine the cosines as like terms, so cosine of 2x is not the same as having 2 cosine x, and it's not the same as cosine squared x, so I can't factor one out. So what do I do with cosine 2x? We refer to that formula sheet that is with that unit circle document. So you'll see down in the double angle section, we've got sine of 2x, and then I have three expressions for cosine of 2x. So we're going to go ahead and take a look at the three variations for the cosine double angle identities. So in the first variation, cosine of 2x is equal to cosine squared x minus sine squared x. So you can see that, that's definitely not the same as just having a coefficient of 2, and it definitely isn't the same as having just cosine squared x. So the double angles do convert into something a bit more complicated trig-wise. So in my first variation, I can replace cosine of 2x with cosine squared minus sine squared x, which looks similar to the Pythagorean identity, except we've got a minus sign instead of a plus sign, and it's not equal to 1. Then in the second variation, we have cosine of 2x, which is equal to 1 minus 2 sine squared x. So notice the similarities between these two. Actually, the differences between all of the right sides of these ones is variations using the Pythagorean identity. So all of these three variations say the same thing, but it's kind of nice how these right sides are set up, either involving both cosine and sine, or just sine, or in the third variation, just cosine. So you can muscle your way through and use any of these three variations, but we're going to see why one of them is a little bit better or easier to use for this problem. So first, I'm going to show you on this separate sheet of paper what this would look like if we replaced the cosine of 2x with the second variation, which would be this one, 1 minus 2 sine squared x. That would give me this expression. So now I have like terms, this one and this one, which would give me negative 1 sine squared x plus 1 equals cosine x. So, this isn't looking good because I have a quadratic trig function, but I have a different quadratic or a different trig function with it. So I can't factor it like using the x method or using normal factoring, and I also can't factor it by taking out a GCF. Now, could I use a Pythagorean identity and convert this into cosine squared? Absolutely, but what we're going to find is that choosing a different double angle variation from the get-go is going to save us a little bit of work. So if I look at the third variation and replace cosine of 2x with 2 cosine squared minus 1, which is the third variation right here. When I look at this expression, yikes, I don't have any like terms that I can simplify, so that's unfortunate. And I have two different quadratic trig functions. So again, factoring would get not so friendly on this one. So this is a big sad face as well. So we are going to choose the first variation of the cosine of 2x identity. So cosine squared minus sine squared x. So similar to what you've done in the past with proofs, sometimes you have to play around with the solving problem to figure out the best way of doing it or how you can actually get to something that makes it solvable. So we are going to choose variation 1, which would give us sine squared x and then plus cosine squared x minus sine squared x equals cosine x. So folks, I don't expect you to have any of these double angle identities memorized, so you'll want to print this off and have it handy when you are doing the test on this unit. So cosine squared minus sine squared x. So there it is. So how is this better than those other two variations that we looked at? Well, look at what happens when we go to combine like terms. Goodbye, sine squared x and minus sine squared x, and we're left with an expression all in terms of cosine. So now I have cosine squared x equals cosine x. So because we have a quadratic, that should push me to try to get the expression equal to 0 so that we can factor it. So I'm going to keep my squared term positive, and I'm going to subtract that cosine x to move it on over to the other side. So cosine squared x minus cosine x equals 0. And how can I factor something like this? Good old GCF. So we're going to take a cosine out of both of those. Cosine x, cosine x minus 1 equals 0. So now, using the zero product prop, we set cosine x equal to 0. We set cosine x minus 1 equal to 0. So now we are ready to look at our unit circle. So I'm going to pull up one of the little ones here. All right, so if I'm looking for where the cosine of x is equal to 0, cosine means we want to find the x value, or the x part of the coordinate that equals 0. So that would be happening here at pi over 2. So remember that our units is radians for this one. And again at 3 pi over 2. So x equals pi over 2. X equals 3 pi over 2. Now, should we add plus 2 pi k to this one? Nope, because we are given the interval of one rotation of the unit circle, 0 to 2 pi. So we don't want to add on 2 pi k because that's going beyond one rotation. So we're not looking for the coterminal solutions here. So pi over 2 and 3 pi over 2. So now, moving on to our second part of the equation. If I add 1, we get cosine x equals 1. So again, looking for an x value. Where does cosine x equal 1? Well, my x value equals 1 only here at 0. Now, we know from our bigger unit circle we've looked at, that in addition to this angle being equal to 0 degrees and 0 pi, it's also equal to 360 degrees and 2 pi. But for this problem, I'm only going to be putting 0 and not 2 pi. Now, why is that? It's because of this interval. So if I go back to my original interval, this says that the angle has to be less than 2 pi, not less than or equal to 2 pi. So 2 pi is not included because it's not on the interval. And we have now solved our first trigonometric problem involving the double angle identities. So again, folks, I chose variation 1 so that I could get this in terms of one trig unit. So when you have the double angle, you must replace it, but you might have to play around with which variation of the cosine that you use to get your units to work out properly. Now, luckily, sine of 2x only has one variation. Tangent of 2x only has one variation. So that makes solving with these ones a bit easier. So let's go ahead and turn the page and move on to our next problem. So first, the instruction says find all, and we're going to add in that word exact, solutions for x. Find all exact solutions for x. And we're going to add on in radians. And on the homework and on the test, it will always specify which you are supposed to use. So finding all the solutions exactly means using the unit circle. And in radians means we're going to be using that for our units. Now, because we aren't given an interval, finding all solutions means we're going to be looking for the coterminal ones too. So from the very beginning, before I actually start doing any of the solving, I would start by defining k. So you must define k. How do we define k? Well, k is going to be equal to the set of all integers. So that is actually part of your solution here. We have to set that k equal to z so that we can add 2 pi k onto our answers. Alrighty, folks, so we start by looking at the setup. We've got sine of 2x minus cosine x. So we see that we have the double angle, so sine of 2x, so we have to replace it. So if I look on my happy little formula sheet, we see that the sine of 2x is only has one variation. So sine of 2x is just straight up equal to 2 sine x cosine x. So we will replace it. So 2 sine x cosine x. Then we've got our minus cosine x. Ugh. So looking at our new setup, this isn't great because, again, we've got two different trig functions, which is like having two variables. So what we are going to do is try to factor. So if you look at this one, is there something we can factor out of both of these? Yes, we can actually take a good old GCF out of both by taking out a cosine x. So take out a cosine x, and that leaves me with 2 sine x minus 1 equals 0. So now, using the 0 prop, either cosine x equals 0 or 2 sine x minus 1 equals 0. And folks, I'm going to encourage you to pause the video here and see if you can find the solutions. And don't forget that you are looking for the coterminal ones as well. So go ahead and pause it and give this one a shot. All right, folks, so where is cosine of x equal to 0? So cosine of x, we're looking for where the x value is equal to 0. That's going to be at pi over 2 and 3 pi over 2. And because I am looking for the coterminal solutions as well, we are going to add 2 pi k. Why 2 pi? Because our units are in radians. So there's 2 of my solutions. And then moving on to the right side here, we add the 1 over. And careful with your signs. Sometimes students get a little sloppy right at the end and they'll say, oh, it's -1 on the right side. So just be careful when you are manipulating these. I do try to show as much work as possible. So then sine x equals 1/2. And then x equals, so sine equaling 1/2, we are looking for where our y part of the coordinate is, a positive 1/2. So where are my y values positive? In quadrant 1 and quadrant 2. We've got a y value of 1/2 here at pi over 6, and then a y value of 1/2 here at 5 pi over 6. So we've got pi over 6 and 5 pi over 6. And then don't forget that coterminal stuff, plus 2 pi k plus 2 pi k. And so for this one, we have found 4 solutions. Will we always have 4 solutions? Nope, not necessarily. As we look back at our other problems, we had 3 solutions on the last one. Only 2 solutions for example 5, 4 solutions for example 4, 4 solutions for this one, 2 for this one, 2 for this one. So it really depends on what the problem looks like. Do you have a quadratic involved? Do you have to square root? So folks, that is it for finding the exact solutions. But in our next video, we're going to be looking at example 8 and how we find approximate solutions.